So the vacuum was a configuration phi 0 was plus or minus V, obviously. Therefore, the vacuum manifold was a manifold of 2 points. And we looked for finite energy solutions, but that required, of course, the energy density to vanish in infinity, but infinity is 2 points, so we can write here M infinity also is 2 points plus infinity and minus infinity in Z. This was really a one-dimensional system with one time and one space. But we said physically what it would mean, just a big desk. That was, and then the vacuum configuration, of course, was this, and then there was a domain ball, phi volt, which was there was also n-type. And this ought to be stable, right? Because what the wall does, we said interpolates between these two minima. There is no way this can sort of make itself become vacuum. But we can actually show explicitly, although it's convincing. It's sort of nice to see that there is a conserved current, which is, and it's trivially conserved. It has nothing to do with equations of motion, right? It's conserved. I am in 2 dimensions. Remember, we are in Z time from our coordinates. Therefore, d mu is 0. So the charge, which is integral of J0 dz, is integral over dz, d phi over dz, from minus infinity to plus infinity. Right? The charge is 0. Component, sorry, here. So it's dz. Correct? And this is phi at infinity minus phi minus infinity. So the charge is 0 for vacuum. It's 2V for wall. And it's minus 2V for an anti-wall. Both wall. If you had any other configuration with the same charge 2V, if you construct that, can be unstable in principle, okay? Then the charge is just wall itself cannot decay. I don't know what we could do to it. I don't want to now imagine it, okay? So this was the picture that emerged, that these spontaneously broken symmetries, when the vacuum manifold corresponds to the infinity manifold, can produce topologically stable objects.
This current that you see, it doesn't come from the equation of motion, but so it doesn't come from another. It's not
right. There is no global symmetry. There is no.
But it's somehow connected to the fact that we can map the manifolds in certain state space.
Yes.
So if we have
it's a topological current, often called.
So
It has to do with, this is often called homotopy, the mapping of one compact object to another.
This charge we are defining, if we want to quantum mechanical, it cannot be some generator of a transformation. It's completely
No, right. It's just sort of counting how you're winding.
Yes, but for example, if we go 4D, we probably can write another expression that is conserved like this, that will give.
We'll see. We'll do the 4-dimensional case. Okay, sure. It will be interesting to see, but it will always something analogous, okay, which will tell us it's going. You can imagine in the case of magnetic monopole, it's going to be magnetic charge at the end.
So this is called topological charge.
It's called a topological charge, right? It's associated with the existence of these classical solutions, or
It measures the winding.
it measures, in a sense, the mapping, if you wish, from one manifold to another. That's what it does. That's the only thing. It tells you whether you have a trivial map. You can always have a trivial map. You have two manifolds, okay? And then I have a non-trivial map when I go around the manifold. In the case of discrete symmetry, it's not so elegant, so beautiful to visualize. It's nicer when we go to more complicated, or if you wish, continuous symmetries in which we are mapping the objects we are familiar with, right? It's sort of funny mapping 2 points into 2 points. But it captures the essence. The interesting thing is, I wasn't sure whether to talk about it, but we have to, because a number of you are interested in cosmology, astroparticle physics, right? That still goes on. Whose thesis is going to be on astro or cosmology? What is it?
Cosmology.
What?
What? Like what?
What will, right?
Oh, I still black hole looks nice.
Well, you don't know yet.
But no, not yet. I know. I still.
Well, with whom?
With Nord.
Uh-huh. You were with Alexei, I remember. Alexei told me, actually I saw Alexei the other day in Munich. It was funny that we ran into each other. We don't see each other here much. See on the road, it's sort of fun. And you will work on neutrino, I presume?
Yeah, solution in the core of the supernova.
Okay. That's not cosmology. So nobody is doing a thesis on cosmology. I saw there was interest.
Dark matter.
Sorry?
On dark matter.
On dark matter. And that's it, right? You know. Ah. Okay. There's also cosmology in axioms. Interesting. So yesterday I was very brief, and I somehow captured, I started thinking I will just mention something that you know, but as if you didn't grasp the essence of Big Bang. That's what I saw yesterday. Was I wrong? I mean, you were sort of not, it was not in your fingers somehow when I asked you, okay? As if, so let's see, there is something in field theory in the case of spontaneously broken discrete symmetries, and we can imagine those symmetries to be, I don't know, parity. I talked of left-right symmetry, CP violation. Actually, the first example was by T.D. Lee, the same Lee of Lee and Yang, in 72, arguing I can break CP spontaneous. Remember, in the CP is interesting because CP is the symmetry that takes particle into an antiparticle. It's for us an exciting symmetry. And in the standard model, can you break CP spontaneously? Spontaneously means that everything is real and the web is complex. Remember, in the standard model, VCKM is complex, you know that. So there must be something complex in the theory. And VCKM comes from quark mass matrices. Quark's mass matrices are Yukawa of the quarks times the vacuum expectation value. This is symbolically written, okay? So this thing has to be complex. So I can ask myself, can I have in the standard model Yukawa real and phi complex? This will be spontaneous CP. If Yukawa is real, lambda is real in the potential, which is not written here, G gauge coupling is real, we will have a CP conserved theory in the beginning to start with, the underlying Lagrange and Hamiltonian, and the CP will be broken spontaneously. So the question is, can I achieve this in the standard model?
This is a complex field, so we can
Sure.
we can direct vacuum.
Remember that by the SQ2 rotation, phi is actually a doublet. I can take this to be 0 in 1, you agree? So I can write V e to the I alpha. That's what I do by the SU2 rotation, you agree? I rotate in this direction. So it seems that I have a phase. That's what Benjamin is saying. I have a phase. This is complex. Is this a phase or not? Remember what a phase is. Phase is something that I cannot unphase. I cannot rotate away, that I cannot eliminate by appropriate transformation. Okay. I just used SU2, but I didn't use hypercharge yet. I can even now rotate more in the third direction. Okay. This phase is not there. That's why I argue. Remember I told you, V is actually real in the standard model. This is not an assumption. This is not the difference by symmetry. You know, it's like when I argue I have these 2 points, phi and minus phi. You can be sure that it doesn't make difference whether I take V or plus V. That will make no difference of what I conclude. The only difference will be if I meet him somehow, and he says that he took minus V, I don't know how we would meet and what that will be. But
the higher representation of Higgs can reach complex.
well, good question, but the standard model Higgs is doublet.
No, but going beyond.
There is no beyond or not. Standard model Higgs is a doublet.
Okay.
So you have to add more Higgses, that's what you're saying, sure.
Yeah, or yeah.
No, they have to add more Higgses. You cannot change the Higgs. Oh, this please, this is now. I'll show you. I thought you knew, but I'll show you. I didn't do that actually. I'll show you a plot how well we have now tested the third generation, for example, Yukawa coupling, and W and Z masses. They fit perfectly with the doublet Higgs. That we shouldn't doubt that. You could say, oh, maybe I don't know, first generation. Well, what could happen, however, that there is another doublet. And now I have to study the symmetry rating. This is the TDL model. Okay. I can't even argue that I put it here in this direction. I have to study it now. In general, I will have here V prime, cosine theta, sine theta e to the I alpha. I don't know. I should start now looking into this, okay? I've used my freedom when I made this real. Now I have to study the potential and I have to see. And he finds out that he can generate the phase spontaneously. It's not surprising.
But the potential term for this new field is somehow...
It's a massive potential with two fields. They are mixed. It's not a potential for a new field. It's a potential now of two fields that interact with each other, okay?
So, for example, in his sombrero potential, we can always rotate in a real V, and since we say that it doesn't make a difference, there is no complex component. But here, in the new potential with two fields...
It's not a question of so much that there is a new potential. Well, it's if the field is within the same symmetry, if I don't have extra symmetry, I cannot rotate. If I rotate, I eliminate this phase. Let me call this beta and gamma. If I make this zero, this won't be zero. If I make this zero, this won't be zero. I can't make both zero. I cannot put two vectors in the z direction. That's all. Remember what we were discussing? When I have two vectors, now I have to study the potential. I have to see under which conditions I could or I couldn't. Of course, he has to be unable to eliminate it. So he will write for you a range of parameters which will show that this phase is actually physical. It's not surprising that you can do that. If you have two vectors, it's not surprising that I can find a situation in which one points here and one points there. You know, think of phases as like directions, okay? So that's a possibility. In other words, discrete symmetries are genuinely interesting physical, potentially realized in nature things, and then it's a very important question to ask. Now, if it's true that I broke CP spontaneously, or P as I claimed in the left-right symmetric theory, then you can ask me, what about these domain walls? What do they do to the universe? So let's talk about it a little bit, okay? Let's do this. The beauty of astroparticle physics, right, is this marriage between particles, standard model field theory, and the Big Bang, if you wish, cosmology. And this is one of the nicest examples. Here there is a lot. This touches into the core of field theory at high temperature. So forget now the physical example. This was en passant. I didn't teach you anything, please. Okay. If you're interested, I'll tell you what you read about TDL. In our case, this is some imaginary discrete symmetry, phi going to minus phi, right? There was a discrete symmetry. Minus precisely symmetric. So there were a number of things I said yesterday very briefly. Let me try to make sense. First, the universe was hot. How hot? How hot was the universe? Okay, let's see what we know and what is speculation. Why do we think that the universe was hot? Why do we think that? Yeah, I know, but why do you think that? Not because someone told you. you don't go back and check whether it was hot, okay? It's getting hotter, they say anyway. We have global warming or even global heating. British Guardian now is using terminology of global heating. It says global warming is not realistic enough, okay? Situation is more dangerous. So it's getting hotter. Today you can feel it. But yeah, it's okay. Sorry for using remark. Nucleosynthesis, the great success of the Big Bang is the nucleosynthesis, which happened at the temperatures more or less. That's a nuclear physics energy, and that's it. MEV. So we know that the universe was hot, that the universe was bigger than MEV. We like to continue speculating that it was even hotter. In the absence of convincing argument that we don't know that, mind you. Actually, many people believe that the universe started with inflation, okay? There is a growing conviction in the how good the evidence is, it's worth thinking about, and we don't know when inflation took place. The universe starts at the moment of inflation. So if this was a time or temperature when inflation took place, this would be the highest temperature that you had realized, okay? But we sort of believe that actually that the temperature goes all the way to T much bigger than the standard model, or even higher. The growing belief in these beliefs often are wrong, okay? So this is how the physics and cosmology of topological difference get related to each other. By belief, the universe was very, very hot. The extrapolation is incredible, by orders of magnitude, okay? We even believe the universe was, I don't know whether I believe it, but I work on that. On what would happen if the universe was so hot that it was above grand unification scale, or even Planck scale, right? That's a long way from MEV. But it's also not so crazy, right? If you live somewhere and you see that when you travel it's similar, you say probably the world will not be so different if I keep doing it. And that's reasonable. So let's take this interesting possibility into account. Then I said yesterday, okay, so let's imagine the temperatures are very high. Let's forget about the limit. Then the third thing very important is and this I only cited, this is a highly non-trivial issue, how to compute the effective potential at high temperature, non-zero temperature. That's a field in itself. I only said, remember what I said, I have some potential, which is that here, for example. It's a negative, I have a tachyonic Higgs at first glance, right? The temperature I said, when you go to high temperature, is the one at zero temperature plus a T squared. When the dust boils, there could be other terms, but the crucial term here, very important, is T squared phi squared. Why is it so important? Because this serves as a mass term. I'm saying this is not surprising that something like this come out, because at a very large temperature, this is the only mass scale. So dimension arguments, when they don't fail, they work. So it turns out that this works, okay? And it's computed, and I remember what I said, due to self-interactions, this is a well-defined field theoretic concept that, and even gauge interactions and so on. So A wants to be positive. If A wants to be positive, then when the temperature is much bigger than the vacuum expectation value of our field, what will happen? Phi will be 0. That's the first thing we started with. When m square is positive, the boring situation that we always imagined before for any field in the world, the minimum is at the origin, and nothing interesting happens. Symmetry remains there. Okay, then I can pause this for a second. If
Is this relation true for any field or?
it's true for any field.
So for the scale, for example, the bosons, how we put like F mu nu multiply by T square or?
If you know mu is a kinetic energy, and kinetic energy is not modified here. I'm just saying that what modifies is the mass term for a particle.
For example, for the field with photon, we cannot put like a mass like mu, so it will give like it will not be gauge invariant.
Right. There are situations where, remember, there was nothing to restore. The photon vacuum expectation value is 0, and photon is massless. You don't have a situation in which, so there the photon would remain massless. U1 was never broken to start with. So what should happen? By the fact that I'm adding some term here, the reason that I can add this term, that this is consistent with all the symmetries in question. This is symmetric. When I compute at high temperature, I should get the terms which are consistent with the symmetry of the light. I'm going to compute with the Lagrangian that I gave. If the Lagrangian is symmetric, under this symmetry, so will the term that I get here. So since U1 is a good symmetry and that fits with the massless photon will remain massless.
So we will not add such a term for the photon.
No, right. We don't add terms, we compute this. This is computed, this is not added, this is computed actually. Weinberg, I have no time to discuss that. You can just think, when am I going to get such a term? When the theory allows you. Photon is massless, that's a U1 symmetry, so that will not change. What will change is that the W will become massless. The opposite will happen. Vacuum expectation value goes to 0. I just convinced you. Take any scalar field in the theory, closing the standard model of X. According to this, at a large enough temperature, phi goes to 0. That implies that all the particle masses in the theory with spontaneous symmetry breaking, like standard model, become 0 at high T. So W and Z become massless. There is no different high temperature. And this is not, when you go to higher and higher energies, then of course the mass matters less. Here there is actually a phase transition. This is not that they matter less. Above some critical temperature, it's like water becoming gas. The phase changes completely. So
it is the point where our potential loses its maximum in the middle.
Right, what was previously maximum becomes minimum. Whether it will happen abruptly or not is a delicate question. I didn't tell you that I know what happens neither. I said when the temperature is much bigger, the study of what happens precisely is highly not trivial. You start thinking, is it a second order first transition, a first order first transition? Remember that the first transition can be defined by the order of the phase transition depending which derivative of the free energies has a jump or not, okay? So there's no sense that we talk about it here. All I want you to tell you how cosmology enters. If you believe, this is, by the way, not so surprising that when you go to high temperatures, people argue. You expect that entropy grows, the systems become more chaotic. And you see, vacuum excitation value is like the order parameter. You have ordered the direction. I have forced my field to be in a certain direction. When I go to high temperature, it's not surprising that the order parameter wants to be 0. System is less ordered if the vacuum excitation value is 0. So people say, I don't even have to do the calculation. That's what Kirchner said originally afterwards. Why do I worry? But okay, I'll do it. I expect And that's why he sat down to look into it. I expect when I go to very high temperature that eventually the idea of thermodynamic chaos will prevail.
But it's counterintuitive because now we have very restoring symmetry.
Right, the symmetry being restored is more chaotic.
But usually it doesn't. Okay,
No, because the order is here is provided by the vacuum excitation value.
Yeah.
That's telling you, in a ferromagnet, it will tell you, it's here, okay? It's choosing a direction, okay? It's ordering the world more. So then the logic goes, the logic number 4. That means, according to this picture, that universe started out in a unbroken phase, and then the temperature dropped down. So let's now go from hot to cold. So let me go now in the opposite direction. I'm at very high temperatures. Okay, the vacuum excitation value is 0, and now the system cools. And so what happens? The vacuum excitation value gets turned on, for example, +3. And then you say, but it cannot be +3 everywhere. The reasoning would be more or less the following. When you have causal connection, okay, I believe that then the system will know about each other, and therefore within what we call the horizon, it is reasonable to assume that the vacuum excitation value points in one direction, but not above the horizon. If 2 points are not in causal contact, so take the point here, imagine the causal contact is up to here. Then you say, I expect here to be -3, randomly. You start drawing, okay? Imagine the universe to be consisting of many horizons. And I reminded you yesterday, this is how it was. Okay? I'll repeat it. Then you said, I expect some random distribution, I'm trying to be random, whatever. Between these are horizons, and this is the universe. Remember the size of the universe is R, is the scale parameter Robertson-Walker-Friedman. That is inversely proportional to temperature, the conservation of entropy. I'll remind you of that, I was quick yesterday. You say, I expect a domain wall to be formed at the level of horizon. That's sort of reasonable, right? It would be a miracle that things get. This is why I speak about the horizon problem. If it was true that this picture looked like that in the early universe, we can't understand. This is how inflation pervaded our field, because they say, how can it be that the universe has one and the same temperature, and me and that guy there were never in the causal contact? That, millions of differently separated regions which have the same temperature, right? That I have to understand. So at this point I say, assuming that this picture was true, I expect to get domain walls. So people study, it's called percolation theory. People take the system of domain walls and try to see what happens. And you will have a situation, for example, when it looks like this. Somehow, when you get a small domain wall, I'm trying to be surrounded. And now I'm trying not to be random. And it's becoming random. So let's try to do it like, imagine the plus is surrounded minus, right? This will be a finite domain wall. Domain wall may not be infinite the way I did it. Domain wall could be like a little everything. Depends how this would happen. And tendentially what happens, these domain walls tend to collapse. Numerical studies indicate. And typically those that are open, start to grow. And the claim is that you would expect at least one domain wall to start growing, okay? Imagine that this is true. Even one. Imagine that we live across the universe. There was a lot of hand waving, right? Everything basically was. Hand waving starts with claiming that the universe was very hot. That's hand waving. This is not hand waving, this can be computed. People did very, very precise calculation with the standard model. They even will tell you what kind of phase transition they expect. People do it by this lattice. When they learn the lattice methods, okay, they can. When you're close to the critical temperature, you sort of enter a stroke coupling regime there, and so on and so forth. But this is sort of established, let's say. Then this is kind of hand waving, right? I'm saying this is natural, that there will be domains, and then domain will have a domain wall. If you accept this, we could try to see what it implies. What was the energy per unit area? You don't have to look at your notes. It's a dimensional argument. This has the dimensions of mass cube. Therefore, this is V cube. Correct? Okay? So what would be the energy of the universe if there is a big domain wall? No, energy of the domain wall would be V cube times R squared. Correct? Everything is 1, pi is 1, and 4 is 1, and so on. I just want to estimate. Let me erase this and let me keep that. What about the energy density of the universe, or energy of the universe? How much energy in the universe? How would I estimate that? Let's see how much cosmology you know. Let me probe it. Let's spend a part of the lecture. I'll remind you what I said yesterday. Think how much of the Big Bang you actually learned. There was an actual course on cosmology, remind me? Paolo gave that. Okay? So what's the energy of the universe?
Radiation dominated. Matter dominated.
Yeah, let me, what do you think?
Radiation dominated.
Uh-huh. Okay? In order to decide that, we have to, it's hard to remember these things. So in order to decide that, we should be able to estimate things very quickly. So how much radiation there is in the universe, or how much of us there are in the universe? What is more?
Dark energy.
Dark energy, I'll come to dark energy. I don't know what dark energy is. Apparently there is 10 times more energy in the universe than what I see. I'll just set this factor of 10. Remember, 10 is 1 anyway. Who cares about 10? I want to see some.
There's more.
That's what we do most of the time with physicists. Right?
So in radiation dominated dark is the T cube is the energy density.
Okay, the energy density of photons is T cube.
We know
We know the temperature, so we know the density. Good. What about the energy density of baryons? In order to know who dominates, how many baryons there are?
we know the number of photons per baryon.
Yeah, what is it?
One baryon per baryon.
Well, if you know one, you know the other, I'm sorry.
Say minus 10. Yeah. Baryon to photons is 10 to the minus 10.
Okay, so n baryons is 10 to the minus 10 temperature of the universe cube. Correct? So energy of baryons is 10 to the minus 10 T energy cube times mass of the baryon. Agree with me? Baryons are very static. They sit in their stars, for practical purposes. This is energy of the baryons. What about the energy of the photons? It's the density times the average times, well, I'm speaking of the energy density at this point. So this is not the, this is epsilon B, right? The energy density. The energy density is the number density times the energy per particle. What about the energy density of photons? Because we are trying to reproduce cosmology, guys. I mean, this is what you should know. You should know this number, and then you should be able to do it immediately. And somehow you didn't do it. You should have done it. What is the average energy of a photon? It's the temperature there. It's massless. So this is T cubed. This is called Stefan Boltzmann law. So let's compare epsilon B over epsilon photon. What is it? 10 to the minus 10 mB over T of the universe. Okay? That's 10 to the minus 10. What is the mass of the barium? That's GeV. What is the GeV? That's 10 to the 9 electron volt. Okay? Why am I doing it in electron volt? Because I remember temperature in electron volt. What do you remember? You have to remember it in some units. And don't tell me in Kelvin. Okay? Because what the hell is Kelvin? Okay? I don't want to hear that. I want you to remember it in some particle physics units. You should get the sense of these numbers. You should know where you live. I know when I ask some of my friends, people that I meet, people from the country, what is the population of your country? And they tell, well, I'm not sure. What's the population of your town? I'm always very surprised. I know precisely, I was always curious. I can tell you precisely what's the population. I'd like to know where I live. So what's the temperature of the universe? Once again, in some particle physics unit. 10 to the minus 4 electron volt. Tech. Great. So what did I get? 10 to the 3. See, photons are irrelevant. It's completely wrong. Who was this? It's Beckman equation. It's completely wrong. There are many of them. The universe is cold. It's so bloody cold. Its temperature is 0 for all practical purposes. Full cosmology. In particle physics units, you can always think of that almost as if you live at 0 temperature. So I can forget about the photons. This is my energy density. And people tell me, you want me to put this factor of 10. Okay. That the energy density of the universe is 10 times epsilon. This is called dark matter claim. Roughly a factor of 10. That's how I remember it. Maybe you know better this number, some of it. I don't remember it very well. Sorry? I think it's not 10, it's almost, well, I don't know. Who cares? I mean, here there are some factors that I didn't worry about. There is 4 pi and so on. I mean, it's sort of silly to be picky here and then not to be picky here. I just want to get an order of magnitude feeling. I want to compare the thing. So what is the energy of the universe? Is energy density of the universe times radius cubed. Correct? Which is 10, and then I look here, 10 to the minus 10. I just want us to have the numbers. T universe cubed, and barium, R universe cubed. This is a domain wall. I could have taken the density, but okay, I took total energy. And this is the energy density of the universe. Energy of the universe, I'm sorry. Okay. We can remember this. Remember what we said. The universe expands like this. When I add TU, I mean today. Sometimes you put a 0 or something. Okay, of course, everything changes. Okay, R changes, the temperature changes. Okay, in this unstable world. And this number is. There are 2 numbers you should know to appreciate what universe is all about. You should know 2 numbers. You must know this number. This is 1 number. Slowly as you hear. Just to get a feeling of. By the way, do you have a feeling how many photons there are in the universe? Really, I don't mean the temperature, okay? What is the density of photons? Per cubic centimeter. I remember I always do everything in centimeter. Million, 2,
400.
great. Even there are 400 per cubic centimeter. It's a lot compared to us, right? I mean, 10 billion times more. So we are almost not there, right? It's interesting. The universe is empty, except for this radiation, practically. Yet, this emptiness dominates the energy. Somehow crazy. You can go forever, you know, before thinking someone else. When you think about it, 10 billion times more photons, but it dominates. So this number, you have a sense of this number, how big it is? I put it 10 to the 30. Let's check it just to see what it is. Well, sorry?
It's outside.
Yeah. Well, we should remember this number, something I have to remember. Or at least we remember these things. So T of the universe is 10 to the minus 4 electron volt, right? That's 10 to the minus 13 GeV. And radius of the universe is, what is it now, 10 to the 10 years, roughly? Am I right? How do you remember it? I remember in centimeters, but you seem to remember in years, so let me do it your way. It's about 10 billion years, right? I think that's correct. So that's 10 to the 10 years. So what's a year?
In what, in seconds?
Right, in seconds.
10 to the minus 7. 10 to the 7.
Yeah.
Pi.
Actually, there is pi, people say, because I should put the pi. I think here, temperature, okay, I won't put the pi. 10 to the 7 seconds. But a second is about 10 to the 10 centimeters.
10 to 24.
So 10 to the 17, actually 3 times, I should put the pi. So it actually becomes 10 to the 8 here in centimeters. Because second is 3 times 10 to the 10 centimeters, right? That's the velocity of light. Okay? I'm using the fact that velocity of light is 3 times 10 to the 10 centimeters per second, which is equal 1. Okay. So I remember it well. It's 10 to the 18 centimeters. Oh, I see. No.
20, it was 20. No,
No,
because
something is wrong.
18,
Wait.
10 to the 18.
There was 10 to the 10 years.
Yeah.
And the years was 10 to the, another 10 to the 18, 10 to the 18. Oh. So this is 10 to the 28. Okay, so I remember it. Well, okay, 10 to the 28 centimeters. So we have 10 to the 28. I'll just write like this, times 10 to the minus 13 times GeV centimeter. The GeV centimeter is 10 to the 13, 10 to the 14, somewhere there. There always this factor of pi enters there also. So you get about 10 to the 28. Which I took roughly 10 to the 30 yesterday. This number is 10 to the 28. To get you a feel for that means that TR cube is almost 10 to the 90. It's the entropy of the universe, the number of particles.
Wow.
It's huge.
I think first we need to consider is what's it called, degrees of freedom, that they change as temperature if we want to really, because it can give
Yeah,
a factor of 100.
sure, there are little things, okay. For example, the way actually the universe looks at some point, the electrons, positrons, and photons were in equilibrium. But then the electron and positron annihilated. However, when I write this T cube, there is a factor which depends on the spin of the particle, or helicity, if you wish, the mass of the particle, okay? That's all of order 1, okay? Which may accumulate it, okay? I may accumulate a factor of 10. The number of photons constantly relatively grew because the other guys, every now and then someone annihilated. Muons annihilated much earlier, so on. W is even earlier. But this is all very rough, okay? We have to be, this is roughly 10 to the 28, okay? This is, when I'm here careless, it's compared to numbers of order 10. This is a huge number. Remember, this is what I told you leads to the horizon picture yesterday. So it's very useful to remember this number. It's close to 10 to the 30. You should somehow remember it, because that's the essence of modern cosmology. That's what led to inflation. Because then the universe, the size of the universe divided by the size of the horizon is 10 to the 28 divided by the temperature, and horizon I said was as t squared. This you must remember. With some effort we could reproduce that in a very little time, but I want you to do that. This should be trivial to reproduce when you are in the radiation-dominated air. You have to remember how the Hubble sphere is related to the density, and G Newton enters. Remember, G Newton has to enter there. It's coming from Einstein's equation, okay? G Newton is implied. And then dimensionally this sort of works. Not 1 over T, this is crucial. That's this strange scale factor. This funny thing which is hard to imagine even what it is, right? In this Robertson-Walker-Friedman metric, it's something strange. This we know what it is, okay? This is how far we see. And then we said that this is 10 to the 28 over M Planck. No, 10 to the 28 is better. Temperature of M Planck. So as the universe gets hotter, this keeps growing and growing. This is called the horizon problem. Okay, you understand why people speak of horizon problem. Of course, this number is 1 today. That's how I define R. I defined R as far as I can see. Okay? Maybe bigger. All I mean that the universe, as far as I can see, when I go down, consisted of myriads of little pieces that were never in causal contact. And this is what is telling us that we expect that there would be this domain ball of gender. It would be a miracle that it doesn't get created. The question is whether it will grow, okay? And now I'm simplifying a picture, and imagine that it did grow and I have a big domain wall. Now you and I can estimate the energy in a domain wall compared to the energy in the... So the scale here is something that is at least the standard model scale. Is there a domain wall in the standard model potential, by the way? Standard model, why not?
Because it's not that discrete symmetry that it's breaking.
There is no discrete symmetry. Well, at first glance, you can think when you write this, okay, the standard model potential is a function of this. There is a discrete symmetry, phi going to minus phi. It's there, but
It's not very broad.
it's not really a discrete symmetry because this is e to the I, I don't know, pi times t3, something like that. This is actually continuous, okay? There is an SU2. This is a center of SU2. This is SU2.
But there is complex conjugation.
So,
That one might be there.
sorry?
Complex
Conjugation
conjugation.
of phi complex.
Like what?
Is that
Which one? There is no more symmetry in the standard model than SU2 times 1. That's very important. That's what we talked about. There is baryon number, there is lepton number, but there are no extra symmetries. Okay, this is very important. We found no extra symmetry in the standard model. There is SU2 cross U1.
I think I need a charge conjugation for Higgs field. Is a symmetry of Higgs potential.
But there is no
Charge conjugation is a discrete symmetry, you're thinking? It's broken as maximally as it can be. Charge conjugation is parity. Remember, charge conjugation takes left to right. In the standard model, it's broken. When I write down the standard model, nu EL and ER, charge conjugation is broken completely. Charge conjugation takes EL into ECL, but that's actually CR bar transpose. And obviously there is no symmetry. This guy is a singlet, this guy is so W breaks it completely. There are no domain walls in the standard model. So therefore there will be some new physics, or maybe the least physics in which you have two Higgs doublets. So I'll take maybe, I would say that V is bigger or equal to 100 GeV. Maybe it's just tomorrow behind the corner, and somehow LHC teaches us that there are two Higgs doublets and it fits within the model. I don't know. But it's not less than this. So what is the energy? So let's, what should we do? I'm not sure how to do it. E domain wall over E universe is 10 to the 6 GeV cube. The radius of the universe, I'll now put the things 10 to the 28 square centimeter square. Okay. Probably if I think a little bit about that, which I had a headache, I would have put these numbers, but I didn't. And this was 10 to the minus 9 GeV, and this number was 10 to the 28 cube. We found out TURU was 10 to the 28 cube. So what do I get? What do I get? This is 10 to the 3, 10 to the 6, no, 10 to the 15. 10 to the 15, okay, times 10 to the, this will, so I will have GeV centimeter square divided by 10 to the 28. Got it a little too big. Maybe it's true. The energy of the universe is 10 to the minus 10, it was, the number density of the baryons, times, this was the density of baryons, this was the energy per baryon. This was 10 because I said there is some dark matter, and this was the size of the universe. It seems correct.
The radius is it when we calculate E of domain one, E of domain one cube R squared, right?
Yes, it's there.
So there has to be temperature into the 28 square.
Temperature. Where?
Squared.
Where?
R squared is into the 28 square over temperature square, right?
No, but we also we compute size of the universe are 10 to the 28 centimeters also.
The size of the universe is 10 to the 28 centimeters. There is this interesting thing that
Ten
means
times
that it's 10 to the 28.
But it's not now, right? It's
It is now.
it's now.
We're
It's
computing.
100 GeV when.
Well, I put everything today. I put RU today. It doesn't really matter because this number is preserved in the expansion of the universe, but I'm comparing the energy of the domain wall today. Imagine it is stable. Remember, it's stable. Okay, you were even convinced yesterday, today we show it from charge. So this is energy density of the domain wall. I thought it was a little smaller. GeV centimeter square is roughly 10 to the 28. It's actually a little less. I mean, GeV centimeter is some number 10 to the minus 14, probably pi times 10 to the minus 14. I remember it is 10 to the minus 14. I can't thing, but there is pi. Okay, so this may be a little smaller. Okay, maybe the number is 10 to the. Who cares whether I made a 10? See, we're now being cavalier. I got a number which is 10 to the 15. If I had got a number which is 100, then I would sit down and put all the numbers correctly back. But when I get 10 to the 15, then I relax. This is correct. Once again, I think this is correct. This is 10 to the 6 from GeV cube. Size of the universe is 10 to the 28 squares in centimeters squared. This is 10 to the minus 9. GeV is the mass of the baryon. T times Ru is 10 to the 28 cube. There are no dimensions here. So everything, if dimensions are correct, everything is correct. I think maybe I go 10 to the 13 sometimes, okay? We can check that, okay? It's huge. The domain wall cannot exist. This is called the domain wall problem. Universe may have 10 times more energy. Okay, naturally it's an energy distribution which is presumably isotropic. Universe and homogeneous works beautifully, okay, but not some crazy thing, okay?
If you put the temperature dependence on the universe radius, I think we got a 1 over t squared for this expression.
But why should I do that? T times R is 10 to the 28. Why do you want me to calculate in a different manner? Where did I go wrong? I don't care how you want to calculate it, okay? Just, this is this.
The E0 is okay, but the domain wall.
Okay, 10 to the 6 GeV cube.
It's always fixed. And that expression is
This is our universe 10 to the 28 centimeters squared.
But for a different temperature, it's like
Which different temperature? I mean, universe today, I put the numbers today.
okay.
What temperature? There is no temperature. This is the formula. What do you mean different temperature?
I was going to argue that for a different temperature of the universe, we might have a different ratio.
At a different temperature, the energy density of the universe, of course, is very different.
That's what it is.
Go enough in time and you will see that the baryons do not dominate. I took it today. Oh, I took it today. No, please. No, you can't think the way you are. If I take it today, this is why I told you that I took a baryon number dominating the universe today. You want to go back in the past, you will find out that there was a moment when the radiation would dominate, obviously. Right? A sufficiently big temperature, there was no doubt that everything was in the form of the temperature, because how big is that the temperature? You have some idea? Okay, the radiation versus matter.
Remember the red sheet. No.
So
1000.
right, must be. Remember what we said? We said that the energy density in the form of baryons is 10 to the minus 10 n gamma times m baryon. Energy density in the photons is n gamma times t gamma. Okay? So they are equal. When they are equal, when 10 to the minus 10 n baryon is equal to n gamma, T gamma. This is the temperature. T gamma is 10 to the minus 1 electron volt. 1,000 times bigger than the temperature today. Anyway, that's obvious because we found out that today there are 1,000 times more, if you wish, energy in the form of baryons than in the form of photons. Okay, you don't remember anything. If you are able to reproduce these formulas, okay, all you will have to remember that R times T is 10 to the 28. And you have to remember something about the universe today. Age, temperature, whatever. I admit. Well, there may be 3 numbers. So you have to remember temperature of the universe, or R of the universe, and then you have to remember n baryon over n gamma. These are the things you have to remember. If you remember them, you can do anything. And you should be able, when you some days when you're doing this cosmology, try to see the forest, don't get out of the cumbersome calculations you did. So domain walls would destroy Big Bang completely. And there have been a number of ways out. One is, of course, is the same solution to the horizon problem. And that is to say, inflation took place afterwards. Okay? At some temperature afterwards. Inflation, remember, eliminates the horizon problem. You didn't study inflation.
This is also called relics of the, I've heard that. So we need inflation so that the energy density of this relic of the domain walls fall, because we don't see them.
It will watch them, but you didn't study inflation, right?
No, we didn't.
Oh, forget it then. So one possibility is inflation which solves the horizon problems, which we will study.
Inflation solves like 3 problems also. Or like,
Yes.
like also the flatness.
Yes, but sure. The degree of the problems of is something that the really serious problem to me is the horizon problem. The others are far less important. Okay. This one is physically, obviously impossible. You cannot have millions of completely separated regions have the same temperature. That is impossible. Something has to be changed. Okay, there are other things which has to do with flatness that we'll see, some kind of naturalness that's not the same issue. Okay, one thing is don't be caught into the naturalness I try to teach you, that someone tells you that I must modify the standard model because the Higgs mass should be much bigger. That's a lousy argument because standard model is a perfectly consistent theory. So why do you say that the Higgs mass should be much bigger? You say, well, the Higgs mass, this is a similar argument, the Higgs mass should be m0 plus some contribution proportional to some cutoff. I believe that cutoff is large and so on. Okay, you start waving your hand. These are not genuine problems. But we won't enter into that. The other possibility, for example, that symmetry may be not restored, as I argued. At least not for the time being. There are counterexamples. Probably the most original work that I've ever done was to show that with Ravi Mohapatra in 1978-9. He was so original that everybody told us we were crazy. Great physicists. It turned out if you look at the 74 paper of Weinberg, unfortunately, he was there in his paper. He realized that there are counterexamples to symmetry restoration. So something like that could happen. Okay. Whatever. I'm just mentioning how it's a very interesting field. When we talk about topological defects, we have very interesting questions. Yes, ma'am.
Why do they assume a universe large domain wall?
No, I said they claim that that's what happens when you have an arbitrary system in this speculation theory. The small one tend to collapse, the closed one, and the open one start growing, and eventually you get one which is, or maybe more, which is as large as the horizon, as the universe. Horizon today, I mean universe today. Okay, that's sort of, all I said, if that happens, we will have a domain wall problem. It may not be so convincing. People argue that the problem may be actually much worse because I may have many more of these objects per horizon, not just one. Okay, there are people who claim that this is sort of a minimum you expect. Some people argue the problem may not be there. Some people argue that it could be much worse. I don't want to talk about domain walls anymore because in the end we don't have really an urgent problem to understand that. The symmetry non-restoration is an interesting thing. And if any of you were interested, that's a beautiful subject. What happens to symmetry breaking at high temperature, which means what happens in the early universe, is obviously a beautiful subject, even if it's speculative. But there is no sense to start something new right now. We should take a break, probably. Am I right? It's 4:10. It's 3:10. We take a break? What do you think? Otherwise I should start speaking about monopoles or answer some question. I don't want to say anything more on this. So we can pause for a few minutes to see if you have questions.
in the case there is like CP spontaneous. So we will have like these patches where like particles dominate and the other where antiparticles dominate, something like that.
So here plus and minus would be the delta CP phase,
Yeah.
would change the sign. So here we would have particles. Actually, there are people who argue in the following manner. They argue.
So
If there was a domain wall in the universe, the argument goes. If the CP violation, or better to say, was broken spontaneously, then I would expect these domains. And then I would expect that there are huge annihilations, they are saying, because particles and antiparticles meet. I don't see such huge sources of annihilation, therefore I conclude that there is no domain wall at the distances bigger and bigger and bigger. That argument is actually lousy, and I think you anticipated yesterday. If you cross the domain wall, you by crossing it, you become whatever is here. You can't cross the domain wall and not be affected by that. Once you come to this side, the phase has changed, and you yourself are antiparticle, okay? So there would be something amazing, okay? I don't know how you would cross it. But by crossing a particle would become an antiparticle, therefore people love to speculate about such things.
and there's also this row of the domain wall, right?
Sorry?
With the domain wall row or the patches where like particle dominates can grow.
This.
Yeah. I don't know if people
Well, I took one,
try to do that.
I cut the universe in half. Just to speak of one, you can think of many if you wish. Sure. And then the claim is that the things tend to grow, depending on the size of the this could be like this, and they say that somehow, it's a random situation, sometimes they like to collapse, smaller one, so there is some critical size, I don't know now immediately how you would define that, and then you will see that some wants to collapse and they are small, the other wants to grow.
So if there is a way like to realize which section are you or you're
No, you can't,
So you-
because by crossing it there,
What
it's
is
like
the-
actually lousy. There could be domain walls without us knowing. I'm amazed that people repeat this argument. We go to meetings and we hear this, that some of us that work on this, and we realize strange argument. Arguing there cannot be such a domain wall because I would see the effect, but you wouldn't see the effect because whoever manages to cross the wall changes his or her personality. By becoming anti, whatever she was.
If these things were to exist, if standard model had a domain wall, they are not like particles because they are not perturbative solutions.
No, they are not perturbative solutions. You will never get it perturbative. How would you perturbatively go from, how would you change this finding perturbatively? Think about it. You stand around the vacuum. That's what we did. We studied around the vacuum. We always found the same situation. Okay, here.
So like, how could we think of interaction of one particle with a domain wall?
Oh, that's an interesting subject. How do you formulate? Now you have to start all over. So you have to now quantize your theory in the background of a domain wall. That's an interesting field theory question. I have not worked on this myself. But you can imagine that's an interesting. First you remember how we work. First you used to do it in the case where phi was 0, and you knew how to do it. Then one day you learned that phi is non-zero. And that was a shock to people because they thought that the guy was a tachyon, and then you realize, no wait, I have to redo everything, and we found out that we could do it. It wasn't that hard at the end. But to show that you can work took a genius of a Hoft. It wasn't trivial to make the theory. So obviously working this out is a beautiful subject. How do I specify, how do I study the motion of a particle in the presence of these defects, especially if they are magnetic monopole, that becomes an interesting issue. So you have to quantize your theory in this background. People, of course, work already thinking, what would happen if I had to quantize my theory in some funny background? People who think geometrically used to study, what if the world is not Minkowski but something else? I have to modify my field theory rules. I'm not working this.
In condensed matter, there is, I think, these things realizing excitations, so like spin waves or over domain walls. I've seen that. So
Yeah, domain walls exist in ferromagnets. Yeah, they realize that in ferromagnets, when you have these transitions by turning off the magnetic field or not, you will not get. You know what happens? You get these domains in the ferromagnets in which you have spins oriented this way and the spin oriented that way, and then there are actually domain walls there. Sure. If these temperatures was not so big that we talk in particle physics, we could imagine talking, studying our own domain walls. This is sort of sad, right? That our scale is so large. That's why it's so hard to do experiments, but cosmology gets even worse. To think about, to understand that the great success of the Big Bang is just a MeV. And for us, in a new modern language of particle physics country, GeV is a small energy. High energies, people think, oh, God, so whatever. Something was occurring, I thought here, but now I wanted to say something else when you were asking, I forgot. Well, maybe it comes back to it. So, half an hour as usual? We go together through I start to the magnetic monopoles a bit? Or not? Or we leave it for tomorrow? Oh, I don't know. Okay, there was a... What do you guys think?
Tomorrow is Friday.
Tomorrow's Friday.
Yeah, tomorrow's fine. Maybe for tomorrow, we have 2 lectures tomorrow. I don't know. Because if we have 2 lectures today, maybe tomorrow 2 lectures again would be.
No, we said we play by ear. We'll decide in real time. So now it's a moment to decide. Let's not think about yesterday and tomorrow. Let's think how we feel today. Are we in the mood to go through? You guys think and then say.
Some of us might need to leave for the second lecture. I don't know if.
Who cannot be? The 2 of you.
Yes, just.
Sorry?
Just
the 2 of you. What about the rest of you guys? I don't know. Should we wait for them for tomorrow, or tell me how you feel? Express your feelings each. Right, just say it. I want today. I want tomorrow. Tomorrow. So we have 3 tomorrow. More. 4 tomorrow. We are still need at least 1 voice more. What? Tomorrow. That's 5. So it's going to be tomorrow. So think about that. If you have some question, then we can take another 5 and 10 minutes. Then let me round it up. Let me make sure that I don't have to come back to this anymore.
These are the same thing as instantons, but in space, right?
Well, instantons is a funny thing. Instantons are classical solution in Euclidean space-time. They are not physical objects that actually exist. Instantons are very funny. So you were saying, why in the world would I talk about instantons, okay? And it has to do with the following. When you do the tunneling from one vacuum to another, in WKB, remember that was something like there was a barrier minus C, something like this, right? dx. Okay, it's 0 energy, there will be just a barrier. Or dz, right? Noting that yesterday we had something like this when we were doing the domain wall. That was actually a square root of E0 dz. Doesn't matter from one point to another, okay? If they're very far from minus infinity to plus infinity. So it turns out you can show that this is actually, this is equal to e to the minus Euclidean action. Of an associated classical solution. I can find you take an Euclidean action, you find out that there will be a solution, okay, that looks like our domain wall, whatever, something like that, what I mean. So it's very interesting to look, in some cases you look at this Euclidean, you're saying, why are you bugging us with Euclidean action? just because you want to study tunneling. Instanton have to do the tunneling from this vacua. Remember that there was actually many different vacua depending on this, how the gauge configuration and affinity, what it does. So they are solutions of the Euclidean action, the minimized Euclidean action. So they are not, strictly speaking, physical objects. You're not gonna. They play an important role in the processes that it's a sort of language. And even when you think about instances and people say, well, how do I do this calculation with instances? One instances, more instances, it's very non-trivial thing to do. So instances, okay, all I can say is are not, the topological defects of immediate physical interest are domain walls, strings, and
but the way we solved it yesterday is very, very similar to our instantons.
yes.
Like we had something
Yes.
in action and we tried to solve by
Right.
energy considerations.
Right. Did I send you the notes?
Yes.
You will see in those notes I discussed that actually. That you could do think of Euclidean action and do that. But domain wall was actually a solution of Euler-Lagrange equations of motions in Minkowski space. There was a static solution. So it was a physical object. I can think of it later on. I can find some analogy with something of a Euclidean action. That's sort of.
But the similarity.
That's just formally speaking.
Okay, similarity comes from the fact that when we solved Euler-Lagrange in our own space, and in our space we have a tan H function, which is a domain wall. If I do for the instanton, I turn t to a spatial variable. I find the same solution, but it's not the space, but the t, one of the variables. So I have to come back to Minkowski, and it becomes a time movement.
Right, but yes, but there is, what I meant is the QCD, there are no such physical objects which have to do when there is a map and you get it in spontaneously broken theories. The topological defects appear when some symmetry is broken, and finiteness of energy requires that when you go far away you live in the vacuum manifold. That provides the map. You require a non-trivial vacuum manifold to get a map. If the vacuum manifold is trivial, if there is no spontaneous breaking, you can imagine that the map is trivial. You map, I don't know, a circle into a point. That's not going to be interesting. It becomes interesting when you map a circle into a circle once or twice or thrice. When n, as you were saying yesterday, is not zero. As Orbek was asking for monopole.
Does instantons, when we talk about instantons, do we always mean 4 dimension, for example? Because yesterday we saw...
No, the language was normally used in QCD in a specific situation, but for example, if you read Coleman notes, he would call instantons any classical solution that minimizes the Euclidean action, which then has no physical implication. He just wants to calculate the tunneling, and then he needs to minimize. You show this for such a solution. So then some people use, depends who. So for example, he would call this instanton. But if you just say instantons to people who are not thinking generally, they will think of a QCD instanton, the original object.
Because yesterday we saw that in 1 dimension it is called kink, I think. In 3 dimension it is...
Right. You can find such objects that play the role of instantons. When they saturate the Euclidean action, okay, they are not physical objects to us. What I was discussing, what I will discuss tomorrow, is actual sort of particle-like. The only thing they extended. You can think of them as fat particles. Okay, monopole. See, the main wall is a bit sort of confusing because it's something very large, but monopole will be very nice. Monopole will look like this. Remember what the domain wall. Domain wall is the Higgs field permeating the inside of that object. That's always true. Okay, you find yourself away from the minimum, Okay, Higgs field is trivial, far away. Remember, we have to live in the vacuum. There is. You have an object in which you have this non-trivial Higgs field inside a little ball. And this produces it turns out, the magnetic field outside. Okay, let's see. Because there are gauge fields in the game, so maybe it's not surprising. Spherical symmetry, it's not surprising. If I have a static solution, then the only thing I will have static potential. Then you expect to get the magnetic field, not the electric field. Because it will come from the potentials that fill this funny ball, okay? So then they're really like particles. They are true physical objects, okay? They are so small, for example, remember what we said, the size is 1 over V? And just to remind you, the V is 100 GeV in the standard model. And GeV, 1 over 100 GeV is 10 to the minus 16 centimeters. But imagine n gat, which is another 14 orders of magnitude bigger, web or smaller. It would be 10 to the minus 30 centimeters, that's 0. So strictly speaking, we would have really particles-like objects. In the first approximation, we would say, who cares about the size? It gives us an idea. We can stop here. Basically, it's the time of the lecture now, and try to respect the time. We can stop here. We want to show that there is a nice solution, that it's not this huge. That's what we'll do tomorrow. Good.